Welcome you all to the third day of online short-term training program on machine learning for societal applications. I am honored and privileged to introduce today's most eminent and distinguished speaker of day 3 session, Dr. H.S. Nagendraswamy, Professor, Department of Studies in Computer Science, University of Mysore. He is currently working as a professor in the Department of Studies in Computer Science, University of Mysore. He obtained his BSc, MSc and doctorate degree in computer science from University of Mysore and has got more than 20 years of teaching and research experience. He visited Shanghai University of China to deliver lectures for BTech courses, Moscow State University, Russia on an Indo-Russian project and presented a research paper. He has presented a paper and chaired a session in one of the international conferences held in Malaysia. He has successfully guided 5 students towards doctoral degree and he is guiding 8 candidates towards doctoral degree currently. He has published 40 plus papers in reputed peer-reviewed international journals including Pattern Recognition Letters, Neurocomputing, International Journal of Image and Graphics, International Journal of Machine Intelligence and Engineering Letters, and international conferences including Asian Conference on Pattern Recognition, Journal of Intelligent Systems, Journal of Multimedia Tools and Applications, etc. He has co-authored a book on C++ and prepared study materials on various subjects for distance education programs of KSOU and University of Mysore. He has been serving as a reviewer for various international journals and conferences. He was the program chair for the International Conference on Cognition and Recognition 2011 and Data Analytics and Learning 2018, organized by DOS in Computer Science, University of Mysore. His area of interest include pattern recognition, image processing, fuzzy sets and theory, data mining, and related areas. With this short introduction, I wholeheartedly welcome our today's speaker, Dr. H.S. Nagendraswamy. I welcome you, sir.
Thank you very much, sir.
So without further delay, I request Dr. H.S. Nagendraswamy to start the session. Over to you, sir.
Thank you very much for having introduced me to the audience. Thank you very much. Distinguished members of the organizing committee, all the dignitaries or online and dear participants. Good morning to each one of you and best wishes for the day. At the outset, I would like to congratulate all the people responsible for organizing this 6 days STTP program on the topic machine learning on societal applications. And also I congratulate all the participants who are responsible for its success. Once again, wishing you the best wishes. I seek the blessings of the Almighty for all the best today. So with this, let me now share the PowerPoint presentation. The topic of my lecture today, as you all know, is a classification techniques. I have already been introduced to all of you, and my mail ID is hsnagendraswamy@gmail.com and hsnswamy@computerscience.uni-mysore.ac.in. You can reach me with these mail IDs anytime for any clarifications or any suggestions and any feedback in any way. So with this, let me begin the session with a beautiful quote. A great thinker was asked, what is the meaning of life? He replied, life itself has no meaning. It is an opportunity to create a meaning. So today we are all having a very good life, and we also have a good opportunity to create such a meaning. So with this beautiful quote, let me go with the technical details of today's presentation. Outline of my presentation mainly covers the topics which gives the basic concepts of a classification and some of the classification techniques which are very popular yet powerful. They are K nearest neighbor classifier, decision tree based classifier, and Bayesian classifiers, followed by a conclusion. I hope in the afternoon session, Professor B.H. Shekhar sir is going to cover few more very important and interesting classification techniques along with a demo of these techniques. Okay. Now let's look at some of the basic concepts related to classification particularly. As you have already learned in the previous sessions on day 1 and 2 by eminent speakers, Professor P. Nagabhushan sir and my friend Dr. Hari Vinod and also Dr. Zahid Ansari. All of them have given a lot of information, the technical content and the basic concepts related to machine learning and machine learning algorithms. In fact, I have also attended the sessions and I understand that the content that has been delivered is very exhaustive and also more informative. And with that, I'm sure that the participants can understand at least to a certain level of detail any machine learning concepts and the algorithms. So with this assumption, let me review some of the concepts, of course, may be already familiar to you. For the sake of completeness and the continuity, I'm just recollecting those basic concepts and continue with the intended technical content today. As we already understand that when it comes to machine learning algorithms, there are three broad categories or classes. One is called the supervised machine learning, also called as classification. Another is called unsupervised machine learning, called clustering. Another one is reinforcement machine learning. In fact, in the previous session, Dr. Zahid Ansari has exhaustively explained the unsupervised machine learning techniques with a lot of applications and the avenues for the future research. And also he has covered most of the basic concepts which can be used in supervised learning techniques as well. Say, for example, the data pre-processing techniques and its importance, and the proximity measures and how the different proximity measures can be used in clustering techniques. The same measures can also be explored for the purpose of classification. And also, he explained the implementation platforms as well. So with all those details, I'm sure that you can easily understand the supervised machine learning as well, and also the techniques. So these techniques are not new to us because in one or the other way, knowingly or unknowingly, all of us are performing these these activities in general in our day-to-day life. You can take many examples. Suppose if you consider a supermarket personnel, they definitely use the classification as well as the clustering techniques in their day-to-day activities within the supermarket. For example, when they first get an item from the vendors, they need to put those items in the respective shelf, which has already been labeled as cosmetics or food items or drinks items or cereals or vessels, anything as such for that matter. So which has already been labeled, And once they get the items from the vendor, they identify that item and put that item into a particular shelf. And that's what is actually a classification. It's not new to us. Or even you can take an example of a vegetable shop. They also use the concept of classification and the clustering. When they purchase the vegetables, they group them and keep them ready for selling. And whenever a new item arrives, they identify and put it in a respective category or a cluster. So this what is actually the classification and the clustering. And similarly, when it comes to reinforcement learning, so we all have subjected to this reinforcement learning when we are studying. And even today also, we adopt this technique. Because when we teach a kid, first we try to explain the kid. Say, for example, I want to teach the alphabets of Kannada or English to a kid. So first I will teach the kid that this letter is called A and this letter is called B, etc. Now, suppose if the kid confuses a particular letter with some other letter, we try to correct it. So whenever it does the good thing, we say, we reward it and we continue it further. Suppose if a kid makes a mistake, we correct it and try to make it right. So this is how we learned the things. The similar techniques can also be used to train the machine. And that's what we call reinforcement machine learning. So these are the three basic machine learning algorithms which we can explore to make machines think artificially and also solves most of the societal problems, or we can explore these techniques to address most of the societal applications or societal problems. So with this brief introduction on various machine learning algorithms, let's continue a particular technique, that is what is a classification. So before I give a very precise definition for a classification, let's look at this image or a visualization where we have a set of trained images like this. In this example, we have some 8 different categories of images which are already used or which are used to train the system. And all these images are already labeled. Say, for example, a smiley, a hand, toy, car, house, wild animals, pet animals, and food. So we are already familiar with these details and we have labeled it, and now we use this to train the machine. Now, how we train the machine? So definitely it requires a little bit of the very basic concepts of like a pattern classification, how to extract the features to represent an object in a machine, and those details. So maybe some of you have already studied those levels of detail, but here I try to cover certain level of detail to make you understand the concepts. So for more details, you can always refer a good material and you can understand the topic to the depth and make the concept very clear and also concrete. Now let's look at how can we understand this particular image or the visualization. Now, as I already mentioned that there are a set of trained images and we have labeled each category with a label. And now we are extracting some features for representing these images in a machine. Because we already know that any high-level concept can also be represented as it is in a machine. We need a corresponding machine level representation for such an object. And such a machine level representation for an object can be called as a feature vector. That means we extract some measurable information from the image and we consider all those measurable and distinguishable information to represent that particular object. That when it comes to an image or a video or any such kind of data. Suppose if it's a text data, so definitely a text is an unstructured data. Again, we need to extract some features from the text, say for example, a bag of words representation, a term frequency, and they are the features which can describe a particular document. So any data which we normally deal at the higher level will be unstructured or not feasible for a machine to interpret and understand and also for process. So we need to convert those text data or video data or audio data or any such type of multimedia data into a form which a machine can understand. And such a process is called feature engineering. We need to extract the features or relevant features from the objects in general, and we have to represent such objects in a machine in the form of a feature vectors. That's what I have mentioned here. So that means each of these images are represented with n-dimensional feature vector. N can be anything. Yesterday, Professor Zaid Ansari was explaining with an example of flower, iris flower data set, where there are only 4 features, F1, F2, F3, and F4. Similarly, any object, any number of features we can consider which found to be feasible, and accordingly we represent that object in a machine, or we can call it as a knowledge base, okay, or a database in general. So that's how all these images are represented in the form of a feature vectors in a knowledge base, and now we have an instance, we call it as a test. So a test instance could be one of these kind images, or even sometimes the test instance may not be available in the database as well. Maybe it's a new object or new instance. Suppose if the instance is already present in the database, or it's closer to the one of the trained images in the database, then how we do the classification? So for example, if I consider this smiley object, then I extract the similar features from such an instance object. I compare with each of these features vectors using any proximity measures which you have already learned in the previous session. Maybe it can be a Euclidean distance measure, or in generally a Minkowski distance measure, right? L norm or city block distance, or a cosine similarity you can use, min-max similarity you can use, or chi-square measure you can use. So any such relevant or a feasible proximity measure can be used to establish the distance or a proximity between the test instance and also with the reference instances in the database. So with this, have this feature vector of n dimension, and I compare with any proximity measure, and I found out the proximity or similarity between the images. Then I find out the label of the category which has the highest similarity with the test instance. So for example, in this example case, we have assumed that we have considered the smiley as a test instance. We have extracted the features. We expect the classification model to produce highest similarity with these set of feature vectors, because this set of feature vectors represent this particular smiley image in the database. So we assign the label for an instance that is a smiley. Similarly, suppose if I consider a hand type of symbol, we repeat the process. I extract the features, I compare with all the reference feature vectors in the database, and definitely your classification model, which has already been trained, should produce you the maximum similarity for this second feature vector, and that is what is the hand shape or object. So likewise, we consider a test instance, extract the features, compare with the reference features already there in the knowledge base, and find out which is the which object has got the highest similarity, and consider the corresponding label, and accordingly we classify. And this is what a very simple concept or the philosophy of a classification technique. I hope you have understand how the classification can be done, or a classification model can be designed with respect to a machine learning concept. So with this understanding, let's move on to the very precise definition for a classification. So with this understanding, I can define a classification as the task of assigning objects to one of the several predefined categories. Because a classification is called a supervised, we are already aware of the class label, which are predefined, as I already mentioned, as an example of a supermarket or a vegetable shop or a drug out inventory and whatever it may be, right? So we have already predefined categories, and what we try to do is we just consider the instance or a test data, and we assign the predefined label to the test instance. That's what classification is, the task of assigning objects to one of the several predefined categories. And this can be visualized as a block box with this diagram. That is, input attribute set X of any dimension. We call it as the feature vectors. And there is a classification model which has already been trained, and that classification model will give you the class label, right? To which class this instance or a test object belongs to. And this is what is the visualization of a classification task. So more precisely, we can define a classification is the task of learning a target function F that maps each attribute set X to one of the predefined class labels Y. So now the very challenging task for a machine learning is we need to identify the best target function that maps the attribute set of an instance object to a predefined class labels. Okay, so this is what is the classification task. Now, if at all I want to make it much more precise from a machine learning algorithm point of view, I think I can give this definition. Given a collection of records, we call it as a training set, where each record contains a set of attributes. One of the attributes is the class. I will show you an example so that you can better understand these definitions. Find a model for a class attribute as a function of the values of other attributes. So the main task is we have to find out the model for a class attribute as a function of the values of other attributes. So the goal is previously unseen records should be assigned a class label as accurately as possible. For example, if I consider a test instance, as I already mentioned, as a smiley, then I should get the accurate label from our model or a classification model, right? So similarly, for any item for that matter, when I input a test or unseen data or an object, and that should be accurately classified, and that's what is expected from any classification model. So it has to satisfy the property of mutually exclusive and exhaustive. So of course, there are other machine learning techniques. We call them as soft computing techniques, where we can assign more than one label for a test instance, okay, in reality. But in a general sense, in a crisp classification concept or a technique, we assign only one label to the test object. Okay, that means either it has to belongs to a class 1 or class 2 or class 3. That's what is called mutually exclusive. We assign a membership value of 1 for that particular test instance where it belongs to one of the classes. So the membership value is 1. But in case of other soft computing techniques like a fuzzy classification, maybe we can assign the degrees of membership. That means the test instance may belongs to 70% to this particular class 1 and 30% to class 2, something like that. Because as all of you have already observed, say for example, a news item classification. When I take a news item classification, so definitely that news item may contain the information or the details about the entertainment like sports or a movie, or it may also contains the information about the politics, or it may contain the information about the agriculture or any other societal matters. If that is the case, so definitely in reality, we can expect the classifier to assign degrees of membership for the given test instance. That means the given test object may belongs to this level of degree, or say for example 70% to a class 1, 30% to class 2, and 40% to class 3, etc., something like that. And we can call it as a fuzzy classification or a soft computing approaches to classification. So definitely in reality, sometimes we have to design a model which mimic the human beings, which is most of the time a fuzzy. Okay, so that is another topic of discussion. Okay, hopefully you can learn those things much later, having understand very clearly the very simple and crisp classification techniques. So with this, now let me put it in a mathematical form. More precisely, a classification problem can be stated as below. Given a database D with Tn number of tuples and a set of classes C, C1, C2, etc., Ck, the classification problem is to define a mapping F from D to C where each Ti is assigned one class. So whenever you are studying any research paper or a textbook, definitely you will find these kind of mathematical notations which can describe a classification task. Okay, so if we understand the basic philosophy of a classification with an example, then definitely we can understand these generalized definition for a classification task. So with an example, we can go to generalization, or from a generalization concept, we can go to the example and we can understand better the task. Okay, so that's what is the objective of this. So note that here the tuple Ti belongs to the database D and is defined by a set of attributes, as I already mentioned. And here I just mentioned as an example here A1, A2, etc., AN are nothing but the attributes, right? So most of the time we use the terminology like attributes or features, okay, so to describe the object. Okay, so we call it as a features, or we can call it as an attributes, or any such meaningful terminologies can be used to describe an object from a machine learning point of view. So having understand these simple definitions and the concepts, now let's illustrate this classification task. That means how can we train a model? What should be the framework of a classification model? Okay, now look at here. As an instance, we have a training set, and in this example we have considered 10 training examples where each example, each sample or an instance consists of 4 attributes. Okay, of course we can consider a transaction ID as well as one of the attribute. Okay, and then but the most important attributes needed for a classification task here are the homeowner, marital status, annual income, and defaulted borrower. Here defaulted borrower is the class label, so whether he is a defaulted borrower or not. For example, in a banking application, the bank officer or a manager wants to know whether this particular customer is a defaulted borrower or not based on the data which is already available with that particular bank or in any other bank. Okay, so in such an instance, we can call it as a class label, where we expect the machine to assign a class label no or S to a defaulted borrower with the details of a customer, like whether he is a homeowner, what is the marital status, and what is the annual income. So this is just an example data, a training set considered only to understand the classification task or a model. Okay, so we have 10 such instances here, where each instance is described with 4 attributes actually. Of course, 3 attributes which are important for a classification task, that is a homeowner, marital status, and the annual income. Okay, so with this data already available, we train the machine, and that is what is the induction, and model will be learned with a particular learning algorithm. And once the model has been learned, then that model can be used or can be applied for a test instance. Now look at here the second table, which is considered as a test set. Now the thing is, for example, if I input the test instance record as a transaction ID number 11, homeowner no, marital status single, annual income 80K. Now with this data, I want to know whether he is a defaulted borrower or not. I want to know, but right now I don't know that, but I want to know. So can my model, a machine learning model, can assist me in labeling with that data whether he is a defaulted borrower or not? And that's what is an example. Okay, so how can we understand this framework? Very simple. To sum it up, we have a training set with n number of instances or samples with the data, and we are going to learn, or we train the model with that data using any learning algorithm, and we call it as an induction, and we learn the model, and now the model is ready. And with this, the test set is used to classify the data as one among the predefined classes, as we already mentioned, okay, by making use of the knowledge which is already trained, okay, with the machine. So with this, now let us continue some of the examples of a classification task. Of course, you can find plenty of examples, but here I have just mentioned only a few. Okay, if you see, you can find plenty of examples, because I already mentioned every day all of us knowingly or unknowingly will do a lot of classification activities, definitely. Okay, so but here just for the sake of completeness, I will be presenting before you some of the classification example tasks. So the first one is predicting tumor cells as a benign or malignant, classifying a credit card transactions as legitimate or fraudulent, classifying secondary structures of a protein as alpha helix, beta sheet, or a random coil, categorizing news stories as a finance, weather, sports, entertainment, and etc. Right? So these are only a few examples. Of course, you can find many such examples where you can use the classification task. So with this, now let's throw some light on some of the issues regarding the classification task. So whatever the classification technique you use, whether it can be a nearest neighbor classifier, or a decision tree classifier, or a Bayesian classifier, or SVM neural network, or whatever may be the classifier. So to get a good performance from any classification model, certain issues need to be addressed. What are those issues? Now let's look at those issues. The first one is called preparing data for classification. That's the very, very important thing. Whether it can be an image, or it can be a text data, or video data, or audio data, whatever may be the data. First, you have to prepare the data for a classification, right? I cannot take the image directly and I do the classification, right? Because that requires some processing in between, right? As you have already seen, the block box of the classification model, that's how we just input the attribute X or an image, and it will give us the predefined label, right? So to perform the task, we need to prepare the data for a classification. The data can be image, text, audio, or video, or any such data. In general, we can call it as a multimedia data. Okay, the first task is the data cleaning. Hope Professor Zahid has already explained this data cleaning in the context of clustering. Of course, the similar data cleaning techniques can also be used here also for preparing data for a classification. The data cleaning means, so we can find out the missing values, or we can find out the outliers, or we can find out the relevance of a particular attribute or a feature for a classification task. So any such kind of task can be considered as a data cleaning. Okay. So any kind of pre-processing. For example, if I consider an image, I want to do some kind of pre-processing, and then I want to extract the features, right? Okay, so that's what is like data cleaning. So the next is the relevance analysis. So not all attributes are relevant for a class. Okay, so hope some of you might have already experienced it. So those who have involved in data mining task or a pattern recognition task, you have already understand the relevance of a particular feature for the task of classification or recognition or for clustering, anything as such, right? So we need to identify the relevance of the data, okay? So that's how, like, for example, a feature reduction or a feature selection, okay? So by doing so, we can enhance the performance of any classifier or a classification task, and also we can reduce the complexity and make the system employable in a real time. So that's what is called the relevance analysis, and that is a subjective, and depending upon what classifier you're going to use and what task of classification you're going to do, accordingly you can define what is the relevance of the particular attribute for that particular task of classification. Another is the data transformation. Sometimes you want to transform the data from one form to another form for better analysis, for better understanding or interpretation, and also for a better learning. Okay, so those who have studied image processing or data mining concepts, so maybe you might have already understand what is meant by data transformation. Otherwise, so I suggest you to refer a particular text in case if it is very much required for your research work or very much relevant for your subject of study. Okay, because all these things will definitely take some time or some level of depth of understanding and analysis. Okay, so at this point of time, I just give you certain level of detail. So the data transformation means the data can be transformed into some other domain. Okay, maybe for example, in case of a principal component analysis, the data can be transformed into the principal components. Okay, or again we can go from spatial frequency to spatial domain to the frequency domain, right, by using a Fourier transformations, right? Or any such kind of transformation we need to perform so that we can keep the data ready for the classification task. And the another very important issue regarding the classification task is comparing classification methods. How can I say that a particular classifier or a classification method is the best method for my task? So definitely when it comes to such kind of comparison, one of the issue is the predictive accuracy. So how accurately the classification model can predict the unseen instance or an object. So accuracy plays a very important role in comparing any classification method, and also whenever you want to apply a classification method for your real-time application, the predictive accuracy is one very important issue you must take into account before employing that technique. The other one is the speed. So for a real-time application, speed also is very important thing, because for example, if at all I want to classify a person whether is something like whether is an authenticated user or not in kind of a biometric technique. So definitely speed is very important. For example, if I go to a ATM and I give my fingerprint, suppose if the ATM has to recognize whether I am an authenticated user or not, then it has to does that particular task within few seconds. That's what is the speed. Suppose if it takes few minutes, then we don't accept such a system. So the speed also plays a very important role in deploying any classification technique in real-time application. So speed is one such issue which we need to consider when we are designing a classification model. Another one is called the robustness. Okay, how stable the classification model is, maybe for a noisy environment or for any such kind of environment, right? How robust it is, that's also one interesting and important issue need to be taken into account. So with this, now, another very interesting and important issue is the scalability. For example, you have designed a classification model which works better. Maybe it can give you 99% of predictive accuracy for a small sized database. Maybe I have some 100 different classes of data, and for that 100 different classes of data, my system may produce 99% of accuracy. But suppose if I add more number of classes, maybe I increase the number of classes to 200, or say for example 1000. Even if that increased scale, whether my classification model will produce the same 99% of accuracy, and that's what is very, very important. Okay, so when we are designing any classifier for our task, we should also keep in mind whether it is scalable or not. So we should always take into account that it has to scale for a considerable sized database. Okay, so these are the 4 important issues when it comes to comparison of classification methods. So let's keep these points in mind and design the classification models which meets these kind of issues. So with this, now let's look at some of the classification techniques. As we already mentioned, several researchers have proposed several techniques for effective and efficient classification of different types of data. We call it as a multimedia data. Among those different techniques, some are very subjective to a particular class of task, and some can be generalized. So accordingly, some of the very popular classification techniques which you can find in literature are the distance-based classifier. So K nearest neighbor is a distance-based classifier which is very simple and very popularly used classifier. Another is called a decision tree based classifier, where we can classify based on certain rules which are visualized as a decision tree. So here ID3, C4.5 card are some of the decision tree based classifiers which are already available, and some of you might have already tried these decision tree based classifiers for your task. And statistical method based classifiers like a Bayesian classifier or regression, they can also be used. And the very popular recent classification techniques are SVM and neural network based classifiers. So we can find many such different types of classification techniques which we can explore for a classification task. So in this lecture, or in my presentation, I try to cover the 3 important classification techniques. As I already mentioned, one is called K nearest neighbor classifier and decision tree based classifier in general, the concepts, and also a Bayesian classifier. So as I've heard that this SVM and neural network based classifiers will be covered in some other sessions. So with this, now let's look at the K nearest neighbor classification technique. I hope majority of the researchers have explored this K nearest neighbor classification technique for the task of image classification or text classification or audio, whatever it may be, because it is a very simplest classification technique we can implement and we can use, right? But for certain applications, it is very powerful, easy to implement as well. So because of that, most of the researchers have explored the importance of this K nearest neighbor classifier. This KNN algorithm stores all the available data and classifies a new data point based on the similarity. I can call it as, in general, a proximity, right? So in majority of the literature, they call it as a similarity, right? So let's use the word called a similarity, okay? So KNN algorithm stores all the available data and classifies a new data point based on the similarity. It is a non-parametric algorithm, which means it does not make any assumption on underlying data like other techniques, right? So maybe in a Bayesian classifier or in some other statistical based classifiers or some other SVM classifiers and etc., where they are called a parametric, where we need to know what is the data distribution. But this k-nearest neighbor algorithm is a non-parametric nature, which means it does not make any assumption on underlying data. It just stores the data in the database. This KNN algorithm is also called a lazy learner algorithm, right? Or instance-based algorithm. Why lazy learner? It will not use a lot of complexities in training the model, other than just storing the feature vectors of the training samples in the data. Apart from that, it does not involve any complex training, something which we use in a neural network classifier or SVM classifiers or NEPSA, etc., something like that. Okay, so in that context, this KNN is called as a lazy learner algorithm or instance-based learning classifier. Now let's look at an example visualization. This is a KNN classifier. I have an input data, say, and in the database, I have some objects which are already trained or used for training a machine, and the predicted output. So in this example, I have shown a cat and a dog. The input data is a cat, which is the shadow of the cat. That's what is the shape. We don't have any color information or the texture information here. Only the shape information is available. Okay. So with that shape information, we are going to do a classification, and your classifier has give us the label, it is a cat. That's what is the predicted output. So when it comes to this, now I just want to tell you that whenever it comes to the features or attributes, so the attributes which are extracted are the features which are extracted from an image or video. They can be a color information or a shape information or a texture information. Okay. So similarly, such features can be, such relevant features can be explored even from a text, audio, and also from video instances. Okay. So depending upon what is the task, we have to decide what the relevancy of the features. So in this example, it is the input data is only a shadow of a cat image. So I can use only the shape features, and with the shape features, I can effectively classify that it's a cat, and your classifier has produced the output, and that's what is the cat. So that's what is the interpretation of this visualization. So now look at this diagram, which gives you some visualization about the principle or working principle of a nearest neighbor classifier. So now we have the coordinate axis x1 and x2, meaning that every point is described with two attributes, x1 and x2, and that's what is a two-dimensional space. Okay. So in this example, we have two images, where in the first image before KNN classifier and the second is after KNN classifier. So what does that mean? What is the meaning of this? So here the image shows there are two categories of samples or data points. We labeled it as category A and category B, where you can see the category A is with a green color and category B is with a yellow color. Now we have a new data point, okay, so which is in blue color, which we consider as an instance or a test point. Now the task of a classifier is whether it belongs to a category A or category B. So this can be achieved through a k nearest neighbor classifier. Okay. So here, now when you look at the second image says that the given data point is assigned to category 1. Now the question is why? Why the classifier has classified the given data point as belongs to category 1? The reason is very simple. By looking at this visualization, you can easily understand that the data point is close to one of the data points in category A when compared to category B. Okay, and because of that, right, if I consider the first nearest neighbor where k is equal to 1, if any one point which is closer to the test sample or instance point, then I assign the corresponding label to that new data point. So in this example, so the new data point has been assigned to the category A. Now let's look at another example instance. Again, a two-dimensional plane x1, x2 are the features describing the data point in a two-dimensional space. We have two categories of data points, category A and category B, and category A is marked as green, category B is blue. Now we have a new data point which is colored yellow. The question is, to which category I must put this new data point, or what is the label, whether it's a category A or category B. Now let's look at here. We have considered the 5 nearest neighbors. Okay, 5 nearest neighbors which are marked with the round symbol or a circle. Look at here. These are the nearest neighbors. 5 nearest neighbors we have considered. So out of 5 nearest neighbors, the 3 nearest neighbors are very much close to the new data point. That's what the category 3 of the points from category A are closest to the new data point, and 2 points from category B are closer to the new data point. By majority of voting, now we can classify the new data point as belongs to category A because of majority of voting, and we can say confidence. Okay, so this is what the principle of a k nearest neighbor classifier. Very simple and easy to understand, implement as well. So similarly, you can consider 7 nearest neighbors or 9, etc. Any number of nearest neighbors you can consider depending upon the feasibility. And of course, there are certain techniques to be, certain analysis need to be made to decide the correct value for k. But in this example, just for understanding, we have considered the 5 nearest neighbors, and with this 5 nearest neighbor concept, the given data point has been classified as category A because there are 3 samples which votes for this new data point. So with this, how it works? It works based on a measure of distance between observations, which I already mentioned as a proximity. It can be sometimes a dissimilarity, or it can be a similarity. It doesn't matter. It all depends on how you implement the algorithm. So in general, we can call it as a proximity, right? So it works based on the measure of the distance between the observations. The k nearest neighbor rule classifies an observation x as follows. Now let's look at the steps followed with this k nearest neighbor classifier. So find the k closest observations in the training data, predict the class by majority vote, choose the class that is most common among those k neighbors. I hope you have understand these statements with respect to the previous example images or the instances which we already explained. And k is a parameter, the value of which will be determined by minimizing the cross validation error later. So while training or whenever we are analyzing the classification model, we can decide empirically what is the best value for a k. Of course, it all depends on what classification task you are going to perform and what data you are going to consider. So all those things matters, right? So k is a parameter, the value of which will be determined by minimizing the cross validation error later. So with this, now, if at all I want to put it in a nutshell, the various steps involved in k nearest neighbor classifier, now we can remember these steps. The first step is store all training data samples in the knowledge base. First thing. So how you do it? Suppose if it's an image, you have to pre-process the image, extract the features and represent the image in terms of feature vectors in the database. Suppose if it's a text, extract the features like the keywords or a bag of words or a frequency term frequency, and represent the documents in the database in terms of the feature vectors. If it's a video, the same process you can follow. If it's audio, again you are extracting some features from the audio signal and you are representing that particular audio in the database. So you have to understand what are the features to be extracted and how those features are represented in the knowledge base. And that is what we have mentioned here. Store all training data samples in the knowledge base. Okay. So the second step is for an input test sample, compute its proximity with all the training samples in the knowledge base and search for the k nearest samples. Okay. I think very simple, easy to understand. For example, in my database, I have 1,000 samples. Now, the test sample or instance need to be compared with all those 1,000 samples. And that is what is one of the major drawbacks of the k nearest neighbor classifier. So whenever the training samples or the database size grows, the performance of a nearest neighbor classifier may sometimes degrade. Okay, or it may take more time to give us the result. Okay, because it has to perform the comparison with all the samples in the knowledge base. Okay, so that's what for input test sample, compute its proximity with all the training samples in the knowledge base and search for the k nearest neighbor sample. Compute the confidence for each class as Ci by k, where Ci is the number of samples among the k nearest samples belonging to class I. So I think you can understand this easily. For example, if there are two classes, as I already mentioned, C1 and C2, and k is equal to 5, right? Now, class 1, we have 3 samples, and class 2, we have 2 samples. I mean, when it comes to the top 5 samples, okay? So out of 5 samples, that is k equals 5, 3 are from class 1 and 2 are from class 2. Explain that with the previous example, right? So accordingly, you can compute the confidence for each class Ci by k, where Ci is the number of samples among the k nearest neighbor samples belonging to class I. Okay, so with this, the classification for the input sample is the class which is the highest confidence, right? Which is the highest confidence, right? So that's how we can perform a simple k nearest neighbor classification for our data, right? Okay, so with this, I hope you understand how a simple k nearest neighbor classifier works. Okay, so having understand the very basic principle of a k nearest neighbor classifier, now let's look at some of the questions associated with this nearest neighbor classifier. How to choose the number of nearest neighbors? Okay, so there is one basic question which comes to our mind. So according to the study, the researchers have given some information that the number of nearest neighbors k should be based on a cross validation or a number of k setting. Okay, you can perform a number of k settings and you do the cross validation, and accordingly you can decide what should be the best k. K is equal to 1 is a good baseline model to benchmark against. Okay, so when you set k is equal to 1, of course, if your classification model works best for k equals 1 for even a large size database, so definitely that's a very good classification model. Okay, so that's what we call k equals 1 is a good baseline model to benchmark against any classification model. A good rule of thumb says that k should be less than the square root of the total number of samples we have considered. Okay, so if the number of training samples is equal to say 100, we can take the square root of that, right? 10 should be the total number of the k nearest neighbors, or k is equal to 10. So generally a thumb of rule says that k should be less than the square root of the total number of training samples. So you can just follow this and you can test your system and if the system works to your satisfaction or to a certain level of accuracy, which is okay for your application, then I think you can decide, yes, that should be the value of k, right? So these are some of the points you must keep in mind when you choose the k value for a nearest neighbor classifier. And now, of course, any classifier will have some advantages and also some disadvantages. So we cannot say that a classifier always gives you the advantages or always outperforms for all types of classification. So we cannot say like that, okay? So different types of classifiers may fit well into certain class of applications. So definitely they do possess certain limitations and also some merits. Accordingly, it is very important for us to assess the merits and limitations of any classifier before we deploy a classification in real time. Okay, so accordingly, let's see some of the advantages and disadvantages of a k nearest neighbor classifier. When it comes to advantages, it is a non-parametric architecture because we already mentioned that it does not involve any assumption regarding the distribution of the data, right? So it's a non-parametric architecture, very simple. As you already understand, it does not involve any complex training, right? Other than just extracting the features and storing those features in the database. Very simple, okay? So take the data. Data can be image, text, audio, or video. Do the feature engineering, means extract the features from such a data and put that in the database. That's all you're going to do in the training stage, okay? So it does not involve any complex training, hence it is a simple. Yet it's a very powerful technique, okay? Because it just involves only a simple matching, right? Take the test instance, extract the features, compare with the reference features in the database, and find out the k nearest neighbors and assign the label of the maximum class, right? I mean, the samples from the maximum class, consider that particular label and assign that label to the instance, right? Class or instance sample. So that's how it is a very powerful for most of the classification applications. And it requires no training time. We already mentioned it's an instance-based classifier. But when it comes to disadvantages, it's a memory intensive and sometimes the classification or estimation may become low, all right, or so slow. So memory intensive, I already mentioned that, for example, if at all I want to store millions of training data, right? So then definitely it is very intensive, right? Okay, for example, I want to store thousands of categories of samples in the database where each 1,000 samples will have 10 instances. So then it is a very memory intensive. And also the classification or estimation will become slow when the database size grows. Okay, so these are the very prominent disadvantages which we can find in a nearest neighbor classifier. Okay, so with this, I hope that you have understand a very simple and a crisp nearest neighbor classification technique, and you can easily implement if you have not yet implemented. Okay, so either you can use a MATLAB or R or Python or even a core programming language like C++. I think you can easily implement this nearest neighbor classifier in any platform, and you can test your model and also for whatever the task you have designed the classification model. Okay, so I have not included any explicit example for this because I understand that it's a very simple and straightforward. Maybe you can definitely try this offline at home and you can understand much more better. If at all you need any such illustrations, I think there are many portals or websites where you can browse through and you can get some examples and you can learn right on your own with this knowledge. Okay, I'm sure you can understand, you can implement, and you can explore the performance of the nearest neighbor classifier. So with this information, I just give you some other dimension, and that's what I just found some research article which has modified the k nearest neighbor classifier, where they call it as they're going to define this function, right, for a classification, right? And also a fuzzy k nearest neighbor classifier. I already mentioned that Okay, so recently the literature has revealed the fact that in many applications, fuzzy based nearest neighbor classifiers may produce a better results, okay, and also more intuitive, right? So I could not find the detailed description about these work, this particular work, because it was not available for a free access and it was published in a Springer. Okay, I will share you the reference of this paper if you are interested, and you can explore, and I think you can get more details about this. Okay, but it's a very simple. I will just tell you how it is simple. Okay, so what you do is have the k nearest neighbor I equals 1 to k. Say k may be, say, for example, 2. Let it be 2, right? There are two classes. Sorry, k equals, say, 5. There are 5 nearest neighbors. And let this j indicates the class label, right? Now, what I do is I take the class label. So here is a crisp classifier. The class label can be either 1 or 0. I consider the corresponding similarity, right? X to corresponding xi. Now, here X is the instance we classified and Xi is the already labeled data sample available in the database. Okay. For example, let us assume that X1, X2 are the class labels. Okay, samples belongs to class 1. X3, X4, X5 are the samples belongs to class 2. Right. Now, what I do is I estimate the similarity between the test instance and the reference instance. I take the similarity and I multiply with the corresponding class value, either 1 or 0, and then I compute the sum. And accordingly, I find out to which class the value is maximum, right? And I assign instance to the class. That's how it works. So similarly, we have another formula where we use a fuzzy, and this is what is the formula for a fuzzy. I think we can interpret a little later. Suppose if we get the paper related to this work, maybe you can explore. It's very easy to understand. But now I will show you one simple example how this KNN or this modified fuzzy KNN works. Okay. Now let's look at an instance here. There are two classes, say C1 and C2. Let k equals 5, nearest neighbors, and S1, S2, S3, S4, and S5 denote the 5 nearest neighbors. Okay, I think now you can easily understand the scenario. Okay, C1, C2 are the two classes, right? K is equal to 5 are the nearest neighbors. Let S1, S2, S3, S4, S5 are the nearest neighbors. If top 2 nearest neighbors are from class 1 and next 3 are from class 2, that is 1, 2 belongs to class 1 and 3, 4, 5 belongs to class 2. Now, our conventional K nearest neighbor classifier will classify the given instance belongs to class 2 because there are 3 samples from class 2 and 2 samples from class 1. Okay, according to this confidence or the majority voting principle, the given instance is classified as belongs to class 2. I think you can understand easily this simple principle. So let the similarity between the test sample and the top 5 nearest neighbors are as follows. Now look at here an example case. The similarity of X means the test sample with S1, that's what the nearest neighbor is equal to 0.5, the first nearest neighbor. And second nearest neighbor S2 is 0.8. Okay, and the third nearest neighbor S3 is a 0.7, and similarly 0.7, X and S4 0.7, X and S5 is a 0.6. Now, with this, our KNN classifier will definitely, according to the formula what I have mentioned in the previous slide, according to this, the given instance X is classified to class 2. Because here we have the membership value 2.1 and this 1.7, and this has the more confidence. Okay, so accordingly, the instance or unseen test sample is classified to class 2, according to this. Now, suppose if I apply the fuzzy nearest neighbor classifier, then it will classify the given sample to category 1 or a class 1. Now look at here the membership value So by using the previous formula, if I compute the membership value, then definitely this says that the given test sample has more membership value, that's 0.657 greater than the class 2, and hence the sample X is classified to category 1 or class 1 rather than class 2. Your conventional K nearest neighbor assigns the test sample X to class 2 in this case, but the fuzzy nearest neighbor classifier will classify the given instance X to a class 1 according to these values. So this is how, but now you can test the performance of the classifier, right? So my suggestion to you is you just implement both the versions of the classification, right? Technique, the K nearest neighbor classification techniques. And for your data set or for your application, you see which one performs better. Suppose if your fuzzy KNN performs better, you can go with a fuzzy KNN, or if your crisp KNN works better, you go with that, right? So it's the subjective, right? So depending upon what data you have, what is the ambiguity in the data, what is the uncertainty in the data, and what is the challenging part of the data, right? Because sometimes what happens now, the intra-class similarity, right? I mean, intra-class variation will be sometimes more than intra-class, right? Variation, right? In inter-class variation, right? So, or you can say intra-class variation is more than between class similarity, right? If that is the case, maybe you need to address such kind of challenging issues in a classification technique, and further, maybe you can explore the fuzzy K-nearest neighbor classification techniques, and that works better than the conventional K-nearest neighbor classifier, right? So it's all up to you to study and decide which works better, okay? So for more details of this fuzzy KNN, maybe later I can share you the reference article with you. You study, understand, and implement it. And if you have any doubts at any point of time, please write to me with my mail ID. I will take positively your queries or your request, and I will help you to clarify your doubts. So with this information on K nearest neighbor classifier, I hope that you have understand, right? And if you have any clarifications, you can, I will try to clarify at the end. Okay. So with this, now let me move on to a tree-based classifier, that is a decision tree-based classifier. Maybe for another 15 minutes, I can cover certain level of detail for this decision tree-based classification. Then we shall have a break, and then we shall continue after the break. Okay. So hopefully for the next 10 to 15 minutes, I will be giving you some of the basic ideas of a decision tree-based classification, and the technical details will be discussed after the break. Now, so this decision tree-based classification technique is another very popular and also very powerful classification techniques that has been explored by many researchers and many applications according to the literature survey. It is a tree-based or a tree-structured classifier where the internal nodes represent the features of a data set, and branches represents the decision rules, and leaf nodes represents the outcome. Because we are already very much familiar with a data structure, a tree data structure, it just follows the tree data structure basically, right? So with this tree data structure, we can include the decision rules, and then we can effectively classify the data sample, right? Or an instance, and whether it belongs to a particular class or not. Okay. Now look at an example visualization of a decision tree based classification technique. Okay. There is a root node, and there is a decision node as an internal node. Look at there are 3 decision nodes, right? And again, the terminal nodes. Okay. So again, here in this example, there is a branch, right, to the left of the tree, or to us, it's the right of the tree. And now, again, it has a decision node, and also we have a terminal node like this. So this is the general structure of a decision tree based classifier. Okay. Now let's see with some more example how this can be better understood. Look at this data. Okay, so I take this data and accordingly we try to understand how the decision tree based classification technique can be used to perform a classification task. Okay, and this data is available over the web. Anybody can find this data if you just Google search. So this is a play badminton data which has been collected for 10 days, observations of the last 10 days. Okay, so there are 10 records. Now the records are numbered 1 to 10, and there are basically 4 attributes, right? And one of the attribute, I mean totally 5 attributes, out of which one is called the class label. That's what is the play, right? The attributes are weather, temperature, humidity, and wind. Okay, and this is called a class label, right? So which has the value no or s. So meaning that suppose if the weather is sunny, the temperature is hot, humidity is high, wind is weak, then can we play badminton? So the data says that you cannot play badminton with this condition. That's what is the meaning. That's what is the knowledge we have with the data which is already available or which has been collected over a period of time. Suppose if the weather is cloudy, temperature is hot, humidity is high, wind is weak, then the data says you can play badminton. Similarly, if the weather is sunny, temperature is mild, humidity is normal, wind is strong, then also you can play badminton. So that's how, what you need to do is, you have to collect the data for training a machine, and accordingly you can train a system, right? So for example, if this is the data, we can train a decision tree, or we can construct a decision tree based on this training data, and then when a new instance arrives with a particular weather, temperature, humidity, and wind information, then I must be able to assign a label whether I can play badminton or not. Okay, so that's what is the classification task, and for this we can construct a decision tree. Right now, let's look at one of the decision trees for this particular task. Okay, so the weather, the humidity, and also wind. Okay, so in this example, for this particular instance, it does not consider the temperature. Okay, why? Now look at here. For example, weather is cloudy, right? So weather is cloudy, you can directly say you can play, right? Weather is cloudy, yes. It's cloudy, and you can yes, right? So the decision is basically when it comes to weather, when it's a cloudy, you can directly say it's a yes. Okay. So that's how. For example, if weather is sunny, right? If weather is sunny, then you cannot directly classify whether you can play badminton or not. You need to consider one more attribute, that is a humidity. And again, with this humidity, you need to consider whether it's a high or a normal. If the humidity is normal, then you can play badminton. If humidity is high, then you cannot play badminton. That's what. So weather is sunny, humidity is high, then you can play, right? So you cannot play. If weather is sunny and humidity is normal, then you can play. So that's how. Similarly, when it comes to weather, if it's cloudy, you can directly say you can play a badminton. If weather is rainy, then you need to consider the wind speed. If it's a weak, then you can play. If it's a strong, you cannot play. So this is how you can construct a simple decision tree for the data which you have already collected as a training data, and with that we can create a decision tree or construct a decision tree, and once the decision tree is ready, then we can classify any given instance. Okay, and we will see how it can be done, but this is just an example I'm going to show you. All right, how we can construct a decision tree for the given data, right, or a training data. Okay, now look at another simple data set here. I think again this is a very popular data set. If you just Google search any classification material, right, related to data mining or anything, you will find this example data wherever you search. Okay? Wherever the data material you get to collect, you will find this. Okay, so that's how I too collected the same data, and now let's see how we can use this data for a training or for constructing a decision tree, and how it can be used for a classification. Okay. Now, as you already understand this data set, it consists of 10 records, 4 attributes, of which one is the class label and 3 are used for decision making, right? That's homeowner, marital status, annual, and defaulted borrower. So homeowner is a binary attribute which has either yes or no kind of value. And marital status is a categorical which has a single, married, and divorced. And this annual income is a continuous attribute where we have 125K, 100, and etc. And defaulted borrower is a class label which can take a value either yes or no. All right. So this what is the training data. Now, how can we construct a decision tree for this training data? So this is one of the decision trees we can construct for this training data. Now look at here. First we have constructed the homeowner, yes or no. Right. If homeowner is yes, directly say is not a defaulted borrower, because look at here, homeowner S, no. Homeowner S, defaulted borrower is no. Homeowner S, defaulted borrower is no. Right. So whenever this homeowner has the value yes, you can directly say that he is not a defaulted borrower. So you can directly say no. With just this value, you can right. You can easily say he is not a defaulted borrower. Suppose if he is not a homeowner, so no. Then what are the possibilities? Then you need to put the marital status as the next attribute. So now look at the marital status. Because the marital status has the 3 values like single, married, and divorced, and here is a binary decision tree constructed. Okay, so either you should consider a single divorced as a one branch, married as another branch, or you can consider single as a one branch and divorced and married as another branch. So you can construct a different types of decision tree for the same data. Okay, that one you should remember in mind while constructing a decision tree, right? So in this example, okay, so when it comes to marital status, no, right? So now look at here, marital status, right? Sorry, marital status married, sorry, marital status married. Now look at here, married, no, married, no, married, no, married, no. So here, even if he is not a homeowner, if the marital status is married, then you can say he is not a default training data. Okay. Now, for example, if he is not a married, then what are the possibilities? He can be a single or divorced, right? Single or divorced. Accordingly, you should consider the annual income. So in this example, the annual income here, in this example, it has taken as a less than 50K or greater than or equal to 50K, right? Accordingly, you can say, you can, whether he is a defaulted borrower or not a defaulted borrower, right? Right. So single, right, and divorce. So for example, single, so 125K, right? Okay. So now look at here, marital status, right? So greater than 80K here, right? So he is not a homeowner, he is not married, and if the annual income, even though he is greater than 80K, he is a defaulted borrower. Okay. So likewise, you can consider here if the annual income is this one, then he is not a defaulted borrower, right? So that's how you can, with the training data, you can construct a decision tree, and then with that decision tree, you can classify then unseen or a test instance whether it belongs to a particular class. So in this example, it's a 2-class problem, whether a defaulted borrower, yes or no, right? So with this, now quickly just see how it has been trained and how it has been used for a classification. Look at here, there is another decision tree which can be constructed for the same data, and that's what I mentioned. You can come out with different decision trees for the same data. So which decision tree is the best, that you have to decide. Of course, with certain researchers have done an extensive analysis on the decision tree, and they have given some information for us, and by incorporating such information, we can always find that the best decision tree for the data. Okay, though there are possible ways of constructing a decision tree, we can arrive at the best decision tree for the data which we consider for training. Now just quickly go through. Now look at this. We have already trained the decision tree. Either you can use this decision tree or this decision tree, whichever you can consider. So accordingly, now we have an instance, right? So what is that instance? The instance says the value homeowner, no. Marital status, yes. Annual income is 80K, yes. Now whether it's a defaulted borrower or not. So given this information, now your system has to label whether it is a defaulted borrower or not. Okay. Now look at this, how it happens. Okay. Now homeowner, no. It comes here. Married, yes, comes here, right? Because it's a married, it can directly go to this, right? Yes, no, to a defaulted borrower. Married, right? Yes. So because he's married, again, now it will not go to the annual income. It will straight away assign no to the defaulted borrower, because you already seen the data set in the previous slide. So we have just seen that if any instance satisfies this path, and definitely it will assign no to the defaulted borrower. Similarly, you can take any other instance, and accordingly that may take you to the other branches, either leaf nodes, and according to the leaf nodes, you can classify the given instance as yes or no, right? The defaulted borrower, yes or no. So this is how you can just understand the working principle of a decision tree. But there are many other issues to be addressed with respect to a decision tree, which we are going to consider now. Okay, I hope you have understand how a decision tree based classifier works. We have the training data, and with the training data we can construct a decision tree. And in fact, there is an algorithm which guides you how to construct a decision tree, and we call it as Hunt's algorithm. And those students who have already studied the data mining subject, you might have already come across that Hunt's algorithm and how it constructs a decision tree. If not, if you are interested, you can refer that book, Hanan Comber, or any material on decision tree, which will tell you how to construct a decision tree. And once a decision tree has been constructed, then the task of classification will be very simple. As we already explained the steps with a simple example, how a decision tree classifies the given instance or unseen sample or a test sample. Okay, so now let's consider some of the design issues of a decision tree induction. Of course, all these design issues have been considered while constructing a decision tree. Okay, now let's look at one by one. And the first important point is it follows a greedy strategy, means split the records based on an attribute test that optimizes certain criteria. That's very important. You cannot simply construct a decision tree without proper understanding. Okay, so you should always understand that the decision tree what you have created optimizes certain criteria. So what is the simple criteria? The simple criteria could be, whenever you give an instance, the instance should be classified with a minimum number of comparisons. Okay, suppose if the tree is very much skewed, then it has to perform several levels of comparison to produce you the final label, and that may not be the best decision tree. So a decision tree should classify an unseen test sample with minimum number of comparisons. Yeah, that could be one of the simple criteria which we need to optimize. Okay, so it follows a greedy strategy. That means it split the records based on an attribute test that optimizes certain criteria. You will see what is that criteria. And the other issues related to this decision tree induction are determine how to split the records. I have just mentioned that you can split based on attribute 1, attribute 2, attribute 3, etc. like marital status, annual income, okay, homeowner. So we just mentioned it in principle, but how to determine and how to split the records. Okay, so that's very important. You cannot just arbitrarily divide the decision tree or split the records. Okay, so that may not yield you the best result. So we should always understand how to split the records. And also we need to determine so when to stop the splitting, right? Okay, so definitely you might have seen in the previous example decision trees, at certain level we reach the leaf node. Okay, once we reach the leaf node, we can stop the decision tree construction or splitting the nodes. Okay, because when we arrived at the leaf node, that indicates that we have already been classified the given test sample as belongs to one of the predefined class, because the leaf nodes always indicates the class label. Okay, so when we reach the leaf node, then we can stop splitting the records or we can stop the decision tree, right? Now when it comes to the split of records in the data for decision tree construction, now there are two questions which arises whenever we want to determine how to split the records. The first question is how to specify the attribute test condition. Here attribute test condition means the feature what we have considered for decision making. I mean, whether I should consider homeowner as a first attribute to split the records, or I should consider a marital status as an attribute to classify the records or split the records. So which attribute should I consider for splitting the records? Okay, so because you have noticed in the previous example that in one branch there is a married, a single and a divorced. In another branch there is a married. I also mentioned that you can consider married and divorced as a one set of attributes and single as another branch. Okay, so there is a possibility that we can split the records based on the attributes. So how to specify the attribute test condition is a question we need to answer, right? And the second question is how to determine the best split. Okay, right? So we cannot simply split the records based on certain attribute. Okay, and we should certain that such a split will always gives you the best result. So the two very important questions associated with determining how to split the records need to be addressed. The first question is how to specify the attribute test condition. The second question is how to determine the best split. Now let us try to find answers to these questions. Okay. Now whenever you want to specify the test condition, definitely we come across the different types of attributes. In the previous session, Zahid has already explained the different types of attributes. I think Professor Zahid Hussain has already explained the different types of attributes, where he also explained what are the proximity measures that can be explored for the different types of attributes, right? So I will not be discussing in detail the different types of attributes here, but I'm just mentioning that whenever you are constructing a decision tree and whenever you have a data which are used to train the system, definitely we can come across the attributes which are of type nominal, ordinal, and continuous attributes. Okay, right? So we need to take into account these three different types of attributes, and accordingly we need to specify the test condition. Okay, so when it comes to number of ways of split, there can be always a two-way split and a multi-way split. In the previous example, what I have presented before you is a two-way split, but you can also go for a multi-way split, right? It is like in our programming language, we use if then else statement or a switch statement. In case of if then else statement, there are two branches. It's a two-way split, a true block and a false block, right? But when it comes to a switch statement, we'll be having a multiple blocks depending upon the case value. It's a multi-way split. Okay, so very similar to that here also for a decision tree, we can split the records based on a two-way or it can be a multi-way split. And I will give you some examples of such two-way and multi-way splits and their pros and cons. Look at here. For example, if we consider a test condition for a nominal attributes, now we have shown some instances here, right? Suppose if it's a marital status, okay, so definitely the values for the marital status attribute are single, divorced, married. In the previous example by decision tree, we considered that single and divorced as a one part and married as another part. That's a two-way split. Suppose if I consider multi-way split, then it will be like this. Let's look at another two-way split examples here. So marital status, so the possible combinations of a two-way split would be, one is married and another is single and divorced. Other possibility could be single, married and divorced. Possibility could be single, married and divorced, right? So now look at here, there are three possible values for a marital status, which is nominal, that is single, divorced or married. Okay, so we can go for a multi-way split, something like this, or we can go with a two-way split. We have possibilities. Now the question is, which is best or this is best, and that need to be studied, analyzed, and then we should consider that for splitting the records. Okay, right. Now let's look at another example case, right, where we have the four values for an attribute, right? Okay, now look at here in this example, there is a shirt size is an attribute. We can take values like small, medium, large, and extra large. There are four possible values for a shirt size. Now, if you go with a multi-way split, then you will be having four splits. One is for small, another is for medium, another is for large, another is for extra large. Okay, suppose if you go with a two-way split, then here are some of the possibilities. There are many other possibilities. I've shown only some possibilities here, right? One is for both the branches, you can consider the two values like small and medium, large and extra large. Meaning that whenever you are splitting the records with respect to shirt size attribute, you are putting all records which are minimum and small and medium into one class, large and extra large into another group. Similarly, when it comes to this example, instance or a split, now we have considered here small as a one branch, medium, large, extra large as another branch. Okay, this means that at this point of time, we are splitting the records where all shirt size with small will go to one class and medium, large, extra large will go to another class. Okay, so similarly, we can understand the third possibilities, small and large will go to one class, medium and extra large will go to another class. So likewise, you can have a possible ways of splitting the records. It could be a binary, or it could be a three-way branch, or in general, we can call it a multi-way branch. So, but the question is, which is best and which maximizes the search criteria? Okay, so are certain criteria. So that we need to consider, and accordingly, we can do that. Split, and we can construct a decision tree. This is one of the important issues. So now look at here, right? Another example. There is an order. First is the small, then is the medium, then is the large, and there is the extra large. So if an attribute takes such kind of values, then we call it as ordinal attribute, because we can always order them in certain sequence. So small is the first, medium is the next, large is the next, extra large is the next in a sequence from ascending to right, or in an ascending order, right? So now the next example is for a continuous attribute. So in the example, what we have already seen, right, there we have one attribute that's an annual income, which is of a continuous. It can take any value within certain interval, right? Okay, so if the case, how to split? So that again, you have to decide the best split using certain criteria. In this example, they have considered 80K, right? 80,000. If the annual income is 1,000, greater than 80,000, then you go to this side. Otherwise, you go to this side, yes or no, right? Similarly, you can also have a multi-way split for annual income. So less than 10,000, one branch, between 10 and 25,000, another branch, 25 to 50, another branch, 50 to 80, another branch, greater than 80, another branch. So this way also you can split the continuous attribute whenever you are constructing a decision tree, right? So as we mentioned, there are three types of attribute that may come across while dealing with the data. That can be a nominal, ordinal, and also a continuous. So here are some examples for all these three categories of attributes. Okay, so with this, now to answer the question, how can we decide the best split? Okay, how can we decide the best split? So some of the measures proposed in the literature by the researchers or explored by the researchers are entropy, Gini, and classification error, right? So these are the measures which you can find for selecting the best split. When you read any research article, or if you are referring any data mining book or a pattern classification book where the classification and clustering techniques are discussed, you will definitely find these measures: entropy, Gini index, classification error. So these measures are defined with this formula. So for more details about this formula and how and etc., etc. So if at all you want that level of detail, so definitely the text has the explanation and also more details about all this. But here my intention is how these measures are explored for a best split. Okay, now let's look at how it can be done. Now look at here an example here at a node. We are considering an attribute, and if the attributes, right, there are two classes 0 and 1. Now we are splitting an attribute, right, a node n1 with respect to an attribute which classifies the records, right, 0 records to class 0 and 6 records to class 1. Now we have labeled here the class as 0 and 1, right? It could be A or B. But in this example, they have taken it as 0 and 1. Class 0, class 1. These are the labels, not the numeric values. These are the labels. 0 is a one class, 1 is another class. Now, when you consider the node n1 and split it, so then you will be having 0 records for class 0 and 6 records for class 1. So with this instance, we calculate these measures with value. Now, Gini index is 0, entropy is 0, error is also 0. So according to this, the entropy, right, and also Gini and error, it says that it is the best. It ranges from 0 to 1. Okay, so I mean, even from negative to a positive, right? So any value extreme, either 0 or 1 could be the best. Okay, so if it is like impurity, so if it is like 0.5 or any other value between 0 and 1, then it indicates what is the level of impurity in the data whenever you are going to do a classification, because you cannot say with one attribute you cannot directly classify accurately, right? So many attributes will have their effect while classifying a instance, right, with many attributes. So we need to decide the best split. Okay, the criteria which is to be minimized here is the minimum value, right? Okay, whichever is minimum, right, and that should be considered. You will see one example. Look at here another instance where at node 2, when you records, right, and that send 1 record to class 0, 5 records to class 1. So with this information, if you come to the Gini index, it shows, right, 0.278. Now the question is how this has to be calculated. It is very simple. According to the formula, 1 minus 1 by 6 square. Now look at here, there are total number of records as 6, of which 1 goes to class 0 and 5 goes to class 1. So 1 by 6 square minus 5 by 6 square, and if you evaluate this, that produces 0.278. And similarly for entropy, we have a formula, right? You can just look at here. This is the formula for entropy. Pi by t log 2 pi by t means the fraction of records which goes to class 1, that is I is equal to 0 to c minus 1, where I indicate the class label. In this example, we have only two classes 0 and 1. So the question is whether how many records goes to class 0, how many records goes to class 1. So accordingly here, 1 by 6 is out of 6 records, 1 record is classified as 0 and 5 records are classified as 1. That's 1 by 6 log to 1 by 6 minus 5 by 6 6, And if we evaluate this, this produces 1.650. Similarly, the error is 1 minus maximum of 1 by 6 comma 5 by 6. Simple, 1 by 6 out of 5 by 6, which is maximum, right? So definitely 5 by 6 is the maximum. I'm going to take 1 minus that value, and that produces 0.167. Now look at here, another case. So node 3, right? So this classifies the records, 6 records, into 2, where 3 records goes to class 0 and 3 records goes to class 1. Accordingly, if we compute the Gini index, entropy, and the error, it produces the 0.5 Gini index, 1 entropy, and 0.5, right? That is classification error. So now, having observed these 3 different instances of splitting the records, okay, so we got value 0 in the first case, 0.278, 0.650, 0.176 in the second case, and 0.51 and 0.5 in the third case. When you look at this, the idea is we have to minimize these values, right? Gini index, entropy, and error need to be minimized. According to these examples, I think this is the best split. Okay, suppose if the node, if it classifies all the records into one class, then that could be the best split, right? Because at that level you will be able to classify, right? So that's what is the meaning here. Accordingly, so the next best split is this. Because when you compare this value with this is minimum. Look at here, 0.278 is minimum compared to 0.5. 0.650 is minimum to 1, right? 0.160 is minimum when compared to 0.5. So the next best is this. And the last one, or the worst among these 3, is this. Right? When equal number of records are put in 2 different classes, and that shows more impurity, right? That's what is the meaning of these measures, the Gini index, entropy, and error. Okay, hope you have understand with these simple examples how these measures can be considered, okay, or computed. Now again, look at here another example, right? Okay, so as already mentioned, right, you can consider this both the 12 records are classified into class 0 and class 1 equally 6. So the Gini index is 0.5. Here the Gini index according to the split, right, 0.486 and also 0.37. So you can just follow the previous equations and just substitute these values into that equation, and you will get the corresponding value. Now look at here an example, car type, where it is a nominal type of attributes, where it takes the values sports, luxury, and family, right? Now we have shown the possible attributes here, I mean possible splits here. One of the splits could be sports and luxury, one branch, family is another branch. Family and luxury is the one branch, sports is another branch, and family and sports one branch, luxury, sorry, this is a multi-way branch, family, sports, and luxury, right? So based on these 3 attribute values, we split that into 3. Now accordingly, suppose if I come to the first type of split, then you will get, right, 9 records classified to class 0, right, and 7 records are classified into class 1, and similarly 1 with respect to family, 3 with respect to class 1. And similarly, when it comes to the sports, this is what is the classification, and with respect to multiple splits, and this is what is the classification, right? So this means, right, okay, at this point of time, so for class 1, with respect to the sports and luxury in a family, 9 will go to class 0 and 1 will go to, right? Look at here. Okay, so 1 according to class 0. Similarly, 7 and 3 likewise. So according to this multiple split, you can just calculate what is the what are the records which are classified into class 0 or class 1, and accordingly you can calculate the Gini index. So the Gini index for sports and luxury is 0.4998, and the Gini index of family is 0.3750, right? Look at here. Okay, for a sports category, right, sports and luxury, we have the Gini index 0.492. How to calculate this? I think I have shown the previous example formula, right? Okay, so according to that formula, you can calculate this. So 9 by 7, sorry, 9 plus 7, 16, right? So out of 16, 9 goes to class 1 and 7 goes to class 2. And similarly, with respect to family, 1 goes to, out of 4, 1 goes to class 0 and 3 goes to class 1. So with these values, if you substitute these values into the formula of a Gini index, you will get, right, for sports and luxury. For this branch, you will get one value, that's 4.4922, and for a family, we get the 0.3750. Now, if you substitute these two values, okay, and if you take the weighted average, you will get the corresponding value, right? The weighted average 16 by 20. So there are 20 records, of which 16 here, 9 plus 7, 16 by 20 into this weight, 4922, and similarly 4 out of 20 with respect to this weight, and that produces 0.468, and that's what is mentioned here, right? Now you understand how this value is calculated with respect to these splits, and that's shown here, and this is for a Gini index. Similarly, you can use the other formula, entropy and classification error, and you can calculate what is the value. So similarly, when you compute the card type in a similar fashion, right? So you will get 0.167, and for this multiple split, you will get 0.163. So having observed these different splits, okay, so according to this particular Gini index, the Gini index suggests that multi-way split is the best a two-way split, because the Gini index for a multi-way split is 0.163, which is minimum when compared to these two, and this indicates that, and this is the best for multi-way split is the best when it comes to Gini index. Similarly, you can calculate the entropy and the classification error, and then you can decide which is the minimum value, and that is for what kind of split, and accordingly you can construct a decision tree. Now, what you understand is, whenever you are splitting the records at any level while constructing a decision tree, you need to take into account these measures. So a Gini index and entropy or error rate, with that you have to minimize the criteria, right? And accordingly you can split. So if you construct a decision tree with these measures, and such a decision tree could perform better at the time of classification, right? Hope you have understand the answer for the question which you have already raised, how to split the records at a particular load while constructing a decision tree, right? So with this, similarly we have another case, right? Because we have already shown an example of a nominal attribute and ordinal attribute, and also another example for a continuous attribute. So how to split the continuous attributes? Because we already mentioned that the attribute value may be continuous, like annual income. If that is the case, how can we split, right? So here you can sort these values, the annual income, according to in the increasing order, and then you have to define the split positions, right? So when you sequence them in a ascending order or a descending order, then you will be having certain interval, like, okay, now look at here, less than or equal to and greater than or equal to greater than 55, less than or equal to 55, and similarly between 55 and 65, right? Okay, and similarly between the interval 70, right, and then 80, right? Look at here, less than or equal to greater than 80, right? Less than or equal to 87, greater than or equal to greater than 87. So likewise, you can just split, okay? So, and with that, you have to calculate how the distribution takes place according to this split for classes yes or no, and according to this distribution, how you can calculate the Gini index. As we already understand how to calculate the Gini index for all these cases. Okay? With these values, for these intervals, you can easily calculate the Gini index, as we have already explained. So with this, so it shows that when you observe the Gini index for these different intervals, this is 0.300, which is minimum when compared to all these, and this indicates that you have to consider this as a less than or equal to 97 and greater than 97, and then you split. Now look at the distribution there after the split. Again, repeat the same process at the subsequent level, right? Applying recursively this idea, and finally you arrive at the leaf node where you have to stop the splitting, right? And that's how you have constructed addition tree. Okay, hope you understand. While constructing addition tree, we may come across different types of attributes like a ordinal, nominal, and also continuous attributes. For each types of attributes, we have to decide which is the best split. Okay, and to decide which is the best split, we should consider the measures like entropy gain and also the error, and which is to be minimized, and at every level you calculate that, and whichever is the minimum, accordingly you decide. And that is what is the guiding principle while constructing addition tree. So with this, now the last point with respect to the addition tree is the stopping criteria. Okay, so the stopping criteria is stop expanding a node when all records belong to the same class. Okay, so hope you have seen in the previous example of humidity case, where in one of the branch after the first level itself, right, all classes will goes to, all records will go to one particular class. So if that is the case, you can stop splitting that particular node. Okay, so because it has already reached the leaf level, you stop at that point. Okay, otherwise you expand and again you recursively apply and stop the tree induction where we reach the leaf level, right, where all records are, the same class or certain criteria have been met. Okay, so that's how you can stop the decision tree construction. So having understand this, I think you can always take a simple example. Okay, and you can work out all these concepts with that particular example, and even you can implement that using core programming languages like C, C++, but today we have a lot of tools, right, as I already mentioned, CART and ID 4.5, etc. So where it supports some built-in functions where you need to just give the data to those tools, so it will automatically does all these things. Okay, in fact, all those algorithms have been implemented, designed and implemented based on these issues and the criteria, right? Okay, but it looks like a black box for us because we'll not be knowing how it has been implemented in that particular language. But what we do is we just give the input data, the system will automatically construct a decision tree, right? And whenever you input an unknown object or an instance or a test instance, the system will automatically follow a decision tree as we just now understand, and finally assign the label to the unseen sample. Okay, so that's how we have a built-in tool which can help us. But if at all we want to design a decision tree for our task or for our data, okay, so these concepts are a must. Okay, so if you understand these concepts, hope you can implement these decision tree classifiers in any core programming languages like C, C++, Java, and you can explore how it works, right? And you can fine tune it according to your requirement, where such flexibilities may not be available in the tools. Okay, when you implement yourself, this you'll be having control over the code. You can fine tune accordingly, and you can come out with the best classifier for your task. Okay, so with this, now let's look at some of the advantages of addition tree classifier. It's inexpensive to construct, as you have already noticed. It doesn't involve much complexity as such, other than just deciding the best splits at every level. Extremely fast at classifying unknown records, because comparing one match and finally you go to the next branch. So it doesn't involve much computation at any point. So extremely fast at classifying unknown records, easy to interpret for small sized trees. So definitely when the data size is big and there are a lot of attributes, means more number of attributes, I mean to say the dimension of the data set is huge, then definitely the tree looks very complex and very difficult to interpret. Okay, so if it's a moderate sized data with less number of attributes, okay, or less dimension, then definitely the decision tree which you have constructed can be easily interpreted. Okay, can be easily interpreted. So that's what easy to interpret for small size data or for size trees. Accuracy is comparable to other classification techniques for many simple data sets. Of course, as we already mentioned that whenever you are comparing one particular classification with some other classification. So definitely it all depends on the data and what type of data you are going to consider and what type of classification you are going to do, right? We cannot generalize this. But of course, for most of the data types, and also, data type, and also for different size data sets, the researchers reveal the technique or reveal the idea that it is comparable to other classification techniques for many simple data sets. So these are some of the advantages we can remember whenever we deal with the decision tree classifiers. Okay. So with this, of course, there are some limitations as well. Okay. So the disadvantages are a small change in the data can cause a large change in the structure of the decision tree, causing instability. I hope you remember in the beginning we have mentioned the robustness of the classifier, right? This is what is an example of a robustness. Okay. For example, if you change the value, okay, or any attribute, so then the whole decision tree need to be altered. So that's what a small change in the data can cause a large change in the structure of the decision tree, causing instability. But you will not notice such kind of instability in case of a nearest neighbor classifier. Okay, so that's how you can compare. For a decision tree, sometimes calculation can go far more complex compared to other algorithm. Of course, when compared to other algorithm, because you need to compute the best split and then you have to decide. So that calculation may sometimes seems to be more complex when compared to other simple algorithms like k-nearest neighbor or other classifiers. So decision tree often involves higher time to train the model. When it comes to large size, so large number of attributes, huge dimension. So definitely it involves more time. Okay, so decision tree training is relatively expensive as complex and time tolerant, right? Taking. Okay, so obviously we should accept it, because for a moderate size or a small size it's fine, but for a large data set with more number of attributes, more dimension, definitely it seems to be complex and the training should be expensive, right? Okay, so that's how, in order to overcome this problem, the researchers have also explored the random forest technique, where the sample size can be reduced, right? And we can construct subtrees for each such sample size, and then we can take the decision of all those trees to make a final decision. And such a concept used in a classification is termed as a random forest classifier, right? Hope you might have already heard that, and some of you might have already used it, or you might have trained it. Okay, but if not, I think you can just go to the literature where you will be able to understand how random forest classifier works. If you understand the basic principle of a decision tree classifier, I am 100% sure that you can study on your own and you can understand the random forest classifier as well. Okay, because it also works with a similar principle, other than ensembling the decisions made by all simple trees to take a final decision. So with this, now hope I can move on to the next classification technique, and that is what is the naive-Bayes classifier. Okay, so let's look at the naive-Bayes classifier, which is another very powerful classification techniques which you can find in the literature. And a lot of people have explored this naive-Bayes classifier for many applications and found to be very, very successful for some type of data. Okay, so now let's look at how in principle it works. Okay, so in principle, if it walks like a duck, quacks like a duck, then it's probably a duck, right? It's a statistical classifier, as we already mentioned. Okay, so now look at here, when it comes to these training samples, right, it walks like a duck, right, and it quacks like a duck. Look at these two samples, right? And these are the two attributes which describes that duck. So if the given test record is a duck, so possibly it matches with this, right? And then you can say it's a duck. Okay, so that's what the basic principle. Okay, let's explore some of the principles and also the decision issues with respect to a naive-Bayes classifier. Okay, so It is a statistical classifier, as we already mentioned, performs a probabilistic prediction. It predicts class membership probabilities, and you will see how it does. The foundation for this Bayesian classification or Bayes classification is the Bayes theorem, which we are going to define in the next slides. The assumptions of these Bayesian classifiers are the classes are mutually exclusive and exhaustive. We have already mentioned that. The attributes are independent given the class. So hence, this is called a naive-Bayes classifier because of these assumptions, and it is empirically proved to be useful and also scales very well. Suppose if you have trained this naive-Bayes classifier for some 100 or 1000 example data sets, even if you add more number of data samples to that or classes, so it says that the survey says that it can scale very well, right? So these are some of the points we must remember when it comes to a naive-Bayes classifier. Now look at here an example naive-Bayes classification data, okay, which is used for understanding a naive-Bayes classification. So this example data set is called air traffic data. You can find this data on web. I have just listed out here also a few samples. So let us consider a set of observations in a database regarding the arrival of airplanes in the routes from any airport to New Delhi under certain conditions. This is what is the use case of the context. Visualization, right? In Delhi, and you can find the flights from all other places to Delhi, and we have some data regarding this particular use case. What is the data? Now this data is called air traffic data, where we have the attributes days, season, fog, rain, and class, that is on time. Now as usual, we have 4 attributes here, out of which 5 attributes, out of which one is the class, right? Okay, the class label. Now these 4 attributes are nothing but days, season, fog, and rain, and these days will take the values. It can be a weekday or holiday or a Saturday. So there are 3 values, nominal values for days attribute, values. Similarly, for a season, we have a spring, winter, and summer and autumn. There are 4 values for a season. For a fog, none, high, and normal. This is the ordinal attribute. Again, this is a nominal, this is a ordinal, right? None, high, and normal. So none, normal, high is the order. So it's 3 values for fog. And similarly for rain, we have none, right, slight, and heavy. So there are 3 values for a rain. So it may not rain, or slightly rain, or it is heavy rain. Okay, so that's how we have 3 possible values for rain and 3 possible values for fog, 4 possible values for a season, and also 4 possible values for a days. And based on these values, which are already collected in a real-time scenario, we have to classify whether it's on time, or it's a late, or very late, or etc. Right? For example, if the weather condition says that it's a weekday, right, and also it's a spring, and fog is none, rain is none, then we can expect the train to land on time or arrive on time. And similarly, if the it's a weekday, the season is winter, no fog, and even though slightly there is a rain, at that point of time also we can expect the arrival of a time on time. So that's how, with some realistic data which we have collected, okay, we have to first train the system. Right here, the class label is on time, late, and very late. Okay, so there are 3 possible classes when it comes to this particular data set. Now look at here, again we have more samples. I think we have 20 samples collected. Okay, 20 samples with 4 or 5 attributes. Okay, out of which 1 attribute is considered as a class label. So here, how many possible values we have for a class? One is on time, another is late, very late. Okay, 3 cancelled. Right. So there are 4 possible class values. So one is late, cancelled, on time, and very late. Okay, so these are the 4 possible classes. So when I give a test instance or a data which includes a particular day, say it can be a Saturday, or it can be an autumn, or fog is none, rain is slight, then what should be the class label? Whether I can expect the flight to arrive on time, or late, or very late, or is it cancelled? And that is what is the actual task of classification. So with respect to this, now let's understand how the naive Bayes classifier works. So here initially I just gave some important points about the naive Bayes classifier, and now we are trying to understand this with respect to an example air traffic data, and with this we are trying to move on to some other basic issues related to naive Bayes classification, and also the working principle of a naive Bayes classifier. Okay, so I just want to highlight some of the interesting features of this particular data, air traffic data, which you can relate for a Bayes classification later. The first is the attributes, the day, season, fog, and rain. So there are 4 attributes. Okay, there are 4 attributes for this data, and another is the class attribute. So with 20 tuples, we already mentioned 20 tuples. The categories of the classes are on time, late, very late, and cancelled. So there are 4 possibilities, ultimately the class. Now, given this as the knowledge of data and classes, we have to find most likely the classification for any other unseen instance. For example, now look at here. It's a weekday, it's a winter, right? Okay, the day is weekday, season is winter, fog is high, rain is none. Now the question is whether the flight is on time or late or very late or cancelled. So that's what is the task classification. So now we see how this Bayesian classifier performs this particular task with respect to this example use case. Okay, now the classification technique eventually has to map this tuple into an accurate class. So that we have already mentioned. So in many applications, the relationship between the attribute set and the class variable is non-deterministic, and that is very important point, and that's what is the challenging thing. Okay, or in other words, a test cannot be classified to a class label with certainty, right? Because when an attribute involves many when the data involves many attributes, just by considering a one attribute value, I cannot certainly classify that sample belongs to a particular class. Okay, so then what to do? In such situation, the classification can be achieved probabilistically. Okay, so we have to consider all the attributes, and based on that, what is the probability that this particular sample belongs to a particular class? So we have to probabilistically estimate the belongingness of a test sample to a particular class. Okay, so that's what is the important point we must remember in case of a Bayes classifier. So the Bayesian classifier is an approach for modeling a probabilistic relationship between the attribute set and the class variable. Okay, because we have an attribute and we have a class, and there is a relationship between these two, and how we have to model that probabilistically. So what is the probabilistic relationship that exists between the attributes and the class depending upon the various values? Okay, so that's what is the main philosophy behind the Bayes classification. So more precisely, Bayesian classifier uses Bayes theorem of probability for classification. Now let's look at some of the theoretical aspects of a Bayesian classification. Of course, we need a little bit of statistics knowledge to understand the naive Bayes classifier. I'm sure that the researchers or the students have already studied or introduced to the basics of probability theory and statistics. Okay, so with that knowledge, I think you can understand some of the definitions which we are mentioning right now. So if not an issue, you can always study, understand, and come back and then you will be able to understand the whole philosophy and working principle of a naive-Bayes classifier, right? So let's see how well we can understand these simple basic concepts, right, or mathematical concepts, which helps us to implement and understand this Bayesian classifier, right? So the first thing is a simple probability. How to define a probability? If there are n elementary events associated with a random experiment of m, of n of them are favorable to an event A, then the probability of happening or occurrence of A is given by the probability of A is equal to m by n. So a simple probability. We are all very much familiar, right? Okay, there are n elementary events. Out of that n elementary events, m events are favorable to a particular event. Then what is the probability, right? It's definitely m by n. Okay, suppose A and B are n2 events, then probability of A and probability of B denote the probability that events A and B will occur respectively, right? And also we mentioned the mutually exclusive events. Means two events are mutually exclusive if the occurrence of one precludes the occurrence of other. The examples for a mutually exclusive events are tossing a coin, two events, either tail or a head events. Okay, so you're already familiar with these things. Okay. So another definition which we need to understand with respect to this probability is the giant probability, right? If P of A and P of B are the probability of two events, then the giant probability of A union B is given by the probability of A plus probability of B minus probability of A intersection B. So this how a giant probability is defined. So if A and B are mutually exclusive, then the probability of A intersection B will be 0, right? If A and B are independent events, then probability of A intersection B is equal to probability of A into probability of B. So these are the very basic and the fundamental concepts related to the probability which we must remember, right? So for a mutually exclusive events, probability of A union B is equal to probability of A plus probability of B, because we just mentioned if it's a mutually exclusive, then A intersection B will become 0, right? So because of that condition, if for mutual exclusive events, it is always probability, giant probability will be a probability of A plus probability of B. So sum of the individual probabilities. Okay. So with this definition, now let's look at another definition. That's what is called the conditional probabilities. Okay. So if events are dependent, then their probability is expressed by a conditional probability. So the probability that A occurs given that B is denoted by probability of A by B. So in our general scenario, most of the times it is a conditional probability because certain events occurs and that depends on some other event. Okay, so there is a dependency, right? I will go to a movie provided if I have a friend who can accompany with me, or I study this if certain conditions are true or certain conditions are applied. Okay, so even most of the times you see terms and conditions apply. So that's what is the real scenario, right? So that's how if events are dependent, then their probability is expressed by a conditional probability. So the probability that A occurs given that B is denoted by probability of A by B. Okay. Now, suppose A and B are two events associated with the random experiment. The probability of A under the condition that B has already occurred, right? That's P of B not equal to 0, because we mentioned that the probability, the event B has already occurred. So then definitely it has certain probability. So it's certainly not equal to 0, right? So in such cases, it is given by the probability of occurrence of A given B is equal to number of events in B which are favorable to A divided by number of events in B, right? I think you can easily understand that there are n number of events related to B. Out of n number of events, B number of events are favorable to A. right? In that case, I call it as a conditional probability. So the probability of occurrences of A given the condition B is simply given by the number of events in B which are favorable to A divided by number of events in B. So the numerator can be expressed as the intersection, right? Number of events favorable to A intersection B, right? Okay, because because we mentioned that number of events in B which are favorable to A means it's an intersection, right? So divided by number of events favorable to B. So that can be denoted as probability of A intersection B by probability of B. So this is how a conditional probability is defined. So I hope you can easily understand all these simple definitions. So having understand the simple probability, giant probability and conditional probability, now let's understand the Bayes theorem. Okay, so because we understand that the foundation for a Bayesian classification is the Bayes theorem, right? So the Bayes theorem says that let E1, E2, En be n mutually exclusive and exhaustive events associated with a random experiment. Okay, if A is any event which occurs with E1 or E2 or etc. En, then this is the formula. So the probability of event E, right, occurs given the condition A, right? Sorry, event A which occurs with E, right? Event A which occurs with E is given by the probability of EI multiplied by probability, right? The simple probability and also the conditional probability. The probability of A given EI, and that's given by the sum of the probabilities of EI multiplied by the probability of A given EI. So this what is the simple Bayes theorem mathematically expressed. Now let's see how it is interpreted. Okay. Now I hope you can understand this Bayes theorem with a simple example illustrations, okay, and also with a numerical example. Okay. Now look at here. With respect to this Bayes theorem, we are going to understand the two terminologies. One is called the prior probability, another is called the posterior probability. Now let's understand that P of A and P of B are called the prior probabilities, and P of A given B and P of B given A are called the posterior probabilities, right? So now let's see the prior versus posterior probabilities. Okay. So we have a table which gives some information to understand this idea. Okay. So the table shows that event Y here has two outcomes, namely A and B. A and B are the two outcomes for this event. Okay. Now, which is dependent on another event X, various outcomes like X1, X2, X3. Now, I think you can understand this problem, right? Or an instance. So we have now two, right, events. Okay, the events are labeled as X and Y. So the event Y depends on X. But now Y has two possible outcomes, either A and B, and that A and B depends on the other outcomes of event X. So this is what is the problem or a modeling. So with respect to this, now let's understand this prior and a posterior probability. Okay. Now, there are two possible cases. The case one is, suppose we do not have any information of event A. Then from the given sample space, we can calculate the probability of Y is equal to A is equal to 5 divided by 10. So there are 10 instances here. Okay, you can just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10, out of which Y is equal to A are 5. Right, look at here, you can just count, there are 5. So the probability, okay, of Y is equal to A, occurrences of A for event Y is 5 by 10, and that is what is 0.5. Now, case 2. Now suppose calculate the probability of X is equal to X2 given Y is equal to A. Now look at here, we have an outcome for event Y, that is A, but that depends on the another event X, possible outcome X2. Now what we need to do is, we have to find out the A and the corresponding X2 with respect to this event, because this Y depends on X. If this is the case, then look at here, A is A here, and look at the corresponding X2. right? So there is a one instance here, okay, and another is A with 3, no, not considered because here it's a 2, and now A is 1, no, not considered, and A is 2 here. So we have a 2 instances, right, where we have event Y with the possible outcome A, which depends on event X, possible outcome X2. So if this condition, we have the 2 instances A with X2 and A with X2. So that's what here for this case. Suppose if we want to calculate the probability of occurrences of an event A with an outcome A with respect to event X with the outcome X2, then the probability is 2 by 5. Okay, because Y is equal to A, there are 5 instances, of which only 2 which satisfies this condition, which depends on X, and 5, and that is equal to 0.4. Okay, so with this, what we try to understand here is later is the conditional probability and the first one is the prior probability, right? And this is called the prior probability and the second one is called the posterior probability. So these prior and posterior probabilities are used for a naive-Bayes classification. If you understand this principle, I'm 100% sure that you can implement the Bayes classifier and you can test your data set, okay, how it performs. So with this understanding, now let's understand the model of Bayesian classification. Okay, suppose Y is a class variable and X is equal to X1, X2, etc. Xn is a set of attributes with an instance. Okay, look at here. Y is a class variable. X is a set of attributes with an instance of Y. Now look at here, right? So with this attribute, the label for that is yi. So this is how we try to understand. So the input is X, consists of n number of attributes. I mean, each instance is described with n number of attributes and associated with each such instance as a class label. That's yi. So with this, now the classification problem is then be expressed as the class conditional probability. How? Okay, so that's how it is defined. Okay, the class conditional probability is given by this formula, right? So what we need to do is the probability of yi given the conditions x1, x2, x3, xn, right? So because for with respect to each of these attributes, we have certain condition, and we need to meet those conditions, and finally we estimate the probability and how well this sample belongs to this particular class. Okay? I think you can understand this model or mathematical concept with an example very easily. Okay? Now, let's back to the data which I already mentioned in the beginning, right? So that is what is air traffic data, which is already mentioned, and also we have described in fact. And now let us calculate the posterior and prior probabilities as explained in the previous slides. Okay, so as we already mentioned, there are 4 attributes, 4 classes, 4 attributes: day, season, fog, and a rain. Okay, for again day and a season, we have these values. Okay, and again for a class, we have a on time, late, very late, and a cancel. Okay. Now, when I observe the data set, which I've already shown in the previous slides, maybe you can try this later. Okay, so there are 14 instances with right on time. There are 14 instances with on time. Okay, where out of which 9 are weekday. Right, I hope you understand. There are 14 instances for on time out of 20, out of which 9 are corresponds to weekday. And that's what is the probability. 9 by 14 is equal to 0.64. Similarly, out of 14 instances for on time, 2 corresponds to Saturday with respect to day. That's 2.14, and 1 Sunday out of 40, that's 0.07, and 2 relates to holiday out of 14, that is 0.14. That is with respect to on-time class. Similarly, with respect to late, we have this. Is the flight is late only on weekday. Okay, so there are 2 instances for a late, out of which one is corresponds to weekday and another is corresponds to holiday, right? But on Saturday and Sunday, according to the data, there is no occurrences of late. I mean, the flight was not late on Saturday or Sunday, according to the data. So the probability is 0. Now, similarly, very late. Okay. So when it comes to very late, according to the data we have, so there are 3 instances of which, right, all the 3 are corresponds to weekday. Right. So very late, the probability is 1. For all other, it is 0. And similarly, for a cancel, right? So according to the data, there is a 1 instance which corresponds to Saturday. That's what is the cancel. The probability is 1, others are 0. So like this, you can understand with the air traffic data how to calculate these probabilities with respect to the attributes day and with these values for season and for a class label. Okay, and continue to this, right? We have other 2 attributes, fog and rain. Values none, high and normal, and none, slight and heavy. So again, with respect to this fog and rain, we have the flight on time arrival. Okay, so when it's none, I mean there are 5 instances corresponds to none, so the probability is 0.36. Meaning that the flight has arrived with a probability 0.6, right, with respect to this attribute none. That means if the fog is none, okay, then the probability that the flight arrives on time is 0.36. Okay, late is 0, very late is 0, cancel is also 0. If the fog is high, the probability that the flight arrives on time is 0.29, late is 0.5, very late is 0.33, and cancel is 1. Look at here, when a fog is high, there is an instance that the flight has been cancelled according to the data which is already available. Similarly, if the fog is normal, the probability of flight arriving on time is 0.36 and late is 0.5, very late is 0.67 and cancel is 0. So likewise, we need to understand the class and the corresponding attributes and the values, and we can calculate the probability, right? We already explained how to calculate the probability. There are 2 cases, right? Prior probability and conditional probability. So accordingly, the prior probability for all these are very simple, because of 20 instances, 14 instances are on time. That's how 14 by 20 is 0.70, right? So out of 20 instances, only 2 instances are corresponds to late. So 2 by 20 is 0.10. Out of, right, 20 instances, only 3 instances are corresponds to very late. That's a 3 by 20 is equal to 0.15. And out of 20, only 1 is corresponds to cancelled, and that's what 1 by 20 is a 0.05. And these are the prior probabilities. So knowing the number of instances and with respect to the corresponding classes, how many records belong to this particular classes without any condition, and that's what is called the prior probability, and we can easily calculate the prior probabilities. Now the prior probabilities is calculated, the conditional probability is calculated, apply these probabilities values for the base formula, and then find out so which class the probability is maximum, right? And classify the given test sample or an instance to that class which has the maximum probability. And that's what is in simple way the principle of a naive-Bayes classifier. Okay, now look at here, how can we do this task? Okay. So given an instance air traffic data, that's a weekday, winter, high, heavy. Now this is what is the actual, say for a season weekday, it's a weekday, I mean for a base, it's a weekday value. The season is a winter, fog is high, rain is heavy. So for this instance, now you need to predict or classify what will be the state. We can expect the flight to arrive late or very late or on time or cancel. So that's what is the task. So now look at here, we have 4 possible cases, right? Because on time, late, very late, and cancel. We have already calculated the prior probabilities: 0.7 for on time, 0.10 for late, 0.15 for very late, 0.05 for cancel. I think we can look at here, right? 0.70, 1.10, 0.15, and 0.05. And that's what we have substituted here. And again, we have the corresponding probabilities, the conditional probabilities here. Okay, with respect to weekday, and for on time, it's 0.64. I think you can verify that. With respect to this winter, with respect to this on time, we have 0.14. With respect to this high, with respect to this on time, we have 0.29. With respect to this heavy on time, we have a conditional probability 0.07. Right? So with this, now if you evaluate this turns out to be 0.0013. And similar calculations for class 2, class 3, class 4, if you do so, then you will get the corresponding probabilities 0.0125 for class 2, 0.0222 for class 3, and 0 for class 4 or case 4. So with this data, what we understand, right? Now look at the probability, the maximum probability, right? The maximum probability among all the 4 cases is delayed. Okay, so if we just write the probability in terms of percentage, that is just 1% in case of on time and 22% for a class 3, that's very late, right? And say for example 12% to case 2 and 0 for case 4, means that is what is cancelled. So with these simple calculations, we understand that the naive-Bayes classifier classifies this instance as late. So with this data, we can say that the flight may arrive very late because it's a weekday, it's a winter, the fog is high and heavy is rain. So because of this, arrival of flight very late, and that's what is the meaning, and that's what the intuitiveness of this classifier. Okay, so hope you understand. Okay, so I think you can just take these example slides which I will be sharing you later, right? You just take a paper and a pencil if you're not already worked out this. I think if you just spend half an hour, you'll be able to understand how this naive-Bayes classifier works with this numerical example. And then you relate these concepts with the basic concepts of simple probability, conditional probability, giant probability, and the Bayes theorem. So if you understand these very basic fundamental concepts, I'm sure that you are done with naive-Bayes classifier. And of course, the additional criteria, conditions, and fine tuning, and that can be learned later when this foundation becomes very comfortable and strong. Okay, so with this, now I hope you can study another example, a very popular example which you can find in many textbooks and also in research articles. Okay, so that's what is the data set. Okay, it has 14 records and it has 5 attributes, of which 4 attributes are used for decision making and 1 attribute corresponds to a class label, that is no or S. It's a 2-class problem, and we have this collected, right? It's related to some commercial application, right? So given some information about a person, age, income, student, and a credit card rating. So the commercial application, right, has to tell whether that person buys a computer or not. Okay, so that's what is the context where this data set has been prepared, right? So here I just tell you some information regarding this. Okay, so if age is less than or equal to 30, income is high, if he is not a student, credit card rating is even fair. According to the data, he says that he is not going to buy a computer. If the age is less than or equal to 30, income is high, student is no, even the credit card rating is excellent, he is not going to buy a computer. Now, if the age group is between 31 and 40 or in this range, if the income is high, the student is no, the credit card rating is fair, then the data says that he can buy a computer, right? Computer buys, yes. Look at the age group here, right? Again, greater than 40 cases, the income is medium and low, right? Student, 1 case no, another is yes. Credit card rating is fair in both the cases. In both the cases, you can expect that the person can buy a computer, yes. That's how with the data we have analyzed under what instances the person buys a computer or not. And this is what is the data that has been collected, and that is the ground truth to train the system. Okay, that's what the training data set. So with this example, now suppose if given an instance, right? Okay, so that's what, if a person with age less than equal to 30, income is equal to medium, student is equal to yes, credit card rate is equal to fair. Now, your Bayesian classifier has to tell you whether with this data about a person, right, whether he is going to buy a computer or not. How can you do the classification? Now, look at here. First, what we need to do is we need to calculate the probability, right? So, probability of X is a computer. Okay, fair probability of X, right? We are going to respect the class CI. That's what, yes. So, I mean, out of 14, okay, out of 14, how many are base computer, right? So, you can calculate the probability here, right? So, as we already explained, with this data set, okay, with this data set, we can calculate the probability with this data set. Now, look at here. Probability base computer is equal to S is 9 by 14. Look at here. There are 14 attributes, of which 9 corresponds to base computer. Look at here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this is known to us and it's independent. Okay. So the probability of base computer is equal to S is 9 by 14 and that is equal to 0.643. So the probability of base computer is equal to no. So out of 14, 9 are base computer yes, and the remaining 5 are no. So 5 by 14 is equal to 0.357. So this is what is the prior probability. Now look at here the conditional probability. The probability of X, right, with respect to the CI. I mean, we know the class label for what values of X, right, we have a corresponding class label. So this is what we need to compute. Now look at here, we have 4 attributes. So probability of age less than or equal to 30. Base computer is equal to yes. There are 2 records. If you just search here, less than or equal to 30, base computer yes, you will find 2 records of 9. Okay? Because here 9 is the event yes. Okay? And now you have a S. Of 9, 2 corresponds to this age less than or equal to 30. And that's what 2 by 9 is equal to 0.222. And similarly, here base computer is equal to no. There are 5 instances, 5 which corresponds to no. Out of 5, with respect to this age less than or equal to 30, there are 3. So 3 by 5 is equal to 0.6. 4 by 9 that is equal to 0.444. So accordingly, you can calculate the probabilities for all other attributes. Okay, I think you can easily calculate this with this particular example. So you can calculate the probability for all the attributes like age, yes or no, income, yes or no, student, yes or no, credit card rating, yes or no. So with respect to this, you can easily calculate the probabilities. Once the probabilities have been created, now look at here, given an instance of this case, so how to classify? Now look at here, for a base computer, yes, we have the probabilities. Now look at here, all red are corresponds to yes, all blue are corresponds to no. Now you just have to multiply this. 0.222, 0.444, 0.667, and again 0.667. And that is what is corresponds to probability of X as a computer is equal to yes. So this X is corresponds to this unseen instance. So this gives us the probability 0.044. And similarly, probability of X and this value base a computer is equal to no, and that is 0.6, 0.4, okay, 0.2 and 0.4. Now this what is the value which we have already calculated, right? 0.6, 0.4, 0.2 and then 0.4, right? Substitute and calculate. So with this, now we got 0.019. So now probability of X base a computer is equal to yes multiplied by probability of base computer is equal to yes. Because we already calculated the prior probability and that's what we have seen in the previous case. Okay, so you multiply that. Okay, so with that you will be able to get 0.0444 and 0.643, and this value with the prior probability, and that's what we have calculated here, 0.64. So just multiply that, you will get 0.028, and similarly for no, you get 0.007. Now, when you compare these two, this tells that this value is greater than this value, and this is corresponds to a person by a computer. So your Bayesian classifier says that with this data, right, according to the training what you already used, the training data, with this instance, your Bayesian classifier classifies the sample as means this data the person by a computer. Okay, so that's how the Bayesian classifier works. I hope these two examples will make it very clear. Okay, so you just explore this example offline, right? And having explored this, 100% sure that you will be able to understand the Bayesian classification. You can implement it very easily in any of the programming languages, right? Maybe MATLAB or with core programming language like C or C++. So with this, I think you can understand how the Bayesian classifier algorithm works, right? Input a set of k mutually exclusive and exhaustive classes, C equals C1, C2, Ck, which are prior probabilities, which we already explained here. We can calculate the prior probabilities. Again, we have a n attribute set A1 to An, for which a given instance A is equal to A1, A2 is equal to A. These are the attributes and these are the instances, I mean the actual values. Okay, so with this, what we need to do is we have to calculate the probability for each class according to this formula. Now look at here. Okay, so with this, I just wanted to highlight a few points about the pros and cons of naive-Bayes classifier. The naive-Bayes approach is very well popular and which often very well explored. However, it has a number of potential problems, so it relies on all attributes being categorical, and if the data is less, then it estimates poorly. So that's one observation as suggested by the experts who have implemented and studied this naive-Bayes classifier. So in conclusion, so here the classification is an extensively studied problem in many applications, and particularly in statistics, machine learning, and many other domains. And classification is probably one of the most widely used data mining techniques with a lot of extensions. And scalability is still an important issue for database applications. Thus, combining classification with database techniques should be a promising topic. Some of the research directions in this context are classification of non-rational data, example, text, spatial, and multimedia data. So there's a lot of scope for the researchers who can explore in the direction. So they can come out with some novel ideas and thoughts and some contributions to the field of data mining, pattern recognition, and particularly in the classification sector. So with this conclusion, I'm winding up the session with a reference. So the materials which I have presented before you so far is extracted from these two textbooks, also from other web sources. So if you just refer these textbooks, sure you will get all these details, right? So hope you have this reference book with you. Okay, if you are interested to study the classification, the data mining techniques. So with this, you can always study, understand, and you'll be able to implement, and you can study further and explore it. So with this, now, I would like to thank the organizing committee, and a special thanks to Dr. Sharmila Madam for having given this opportunity for me to share my little knowledge on the topic classification techniques, particularly the supervised classification techniques. And I must also thank all the participants for your interactive participation, as I was just observing here. Okay, so if you have any questions, if time permits, I can take up your questions right now, or else, as I already mentioned, my mail ID, you please write to me. I will sincerely attend your questions and try to address your questions and try to help you in any way possible based on whatever the knowledge I have. So once again, I thank each and everyone for this, who supported this session, and also the organizing team. Thank you very much.
Thank you, sir. Such an excellent conceptual session on various classification techniques. So dear participants, we have come to the end of a morning session of day 3, and we have few questions, sir.
Yes, sir.
So first question, which is the best tool for implementing the classification algorithm?
Sir, actually, we have not explored any such specific tools, sir. But recently, some tools are available. In fact, I have not explored those tools. I think as the sir has already mentioned in the previous sessions, like there are a lot of tools like MATLAB environment or R Studio. I think all those tools will support these built-in functions for this, and you can explore that, and you can even study how these tools can support the implementation of all these classification techniques. But my suggestion to the researchers is, if they implement these concepts right using a core programming languages like C and C++, they will be able to understand in depth all these ideas. So
Yeah.
to be able to understand all these ideas, and accordingly, they will be having a complete knowledge about those techniques, and they can fine tune accordingly, right? So that's what is my suggestion, sir. Okay, so of course they can find a lot of other tools for implementing any of these ideas. So maybe they can use a MATLAB, or they can use a Python, or they can use R Studio, where some built-in support will be there. But however, my suggestion to the students is, because they are all something like a black box. Okay, what they do is they just input the data and they just set some parameters, and with that they are going to perform the task. But if at all you want to understand in depth, so definitely implementation with a particular programming language like C or C++ is always suggested, so that they will have more confidence and they can fine tune it according to their need, and even they can extend that idea for any other subjects, like it can be a non-relational type of data or a multimedia data and many other different types of data, sir. Okay.
So how do you decide the best classification model for image segmentation?
So for image segmentation, actually the image segmentation uses a unsupervised classification technique. And of course, here, if at all you want to label in advance, this is the particular region I want to segment. Okay. So, but again, we need to explore which is the best technique. Okay. Because depending upon what features you are extracting and how those features will best fit into a particular model. So that needs to be studied, because we cannot generalize a particular task. It all depends what is the complexity of the image, right? And what features we are extracting and how it can be modeled. So all those things plays a very important role. I think it is subjective. Maybe it's very difficult to generalize those ideas, and I can say directly you can apply this and you will get a good result. However, if you have already experienced with one or two examples, maybe with that example I can say, yes, for this task you can apply this. But right now we have not tried that those techniques, and we have explored, right? So maybe it's always there is a scope for the researchers to make use of the existing tools, right? And they can try and they can compare, and then they can decide which is the best tool.
Thank you, sir. So I, Professor Muhammad Hafiz MK, on behalf of Department of Computer Science Engineering, EA College of Engineering, feel privileged to wholeheartedly extend my gratitude of having Dr. H.S. Nagendraswamy, Professor in Department of Studies in Computer Science, University of Mysore, as the speaker of today's session. I am sure the participants will definitely try creating and defining a beautiful meaning for their research life from the highly informative session shared by you, sir, and also help them explore the higher dimensions related to the topic. I once again thank Dr. H.S. Nagendraswamy for sparing few valuable moments from his highly busy schedule and delivering a wonderful session on clustering techniques. And also, we look forward for your support and cooperation in future events too. Thank you very much, sir.
Thank you very much, sir.